Hello everyone, I'm Anand Choudhary from BTech Engineering Physics third year at IIT Roorkee, and today I would be talking about statistical signal processing. To begin with, let me motivate the study of this topic. That is, why do we need to study and discuss about statistical signal processing in the first place at all? What we have been used to dealing with now are deterministic signals. A deterministic signal is one that is a completely specified function of time. In other words, for any given value of the input parameters of that particular signal, we know its output value, and thus a deterministic signal can clearly be represented by a mathematical function for each and every given instant of time. So as you can see in this particular GIF, a pure sinusoid can easily be represented by a mathematical function, say a sine omega t plus phi, and as a result it is a deterministic signal. Deterministic signals, however, are only found theoretically. It is extremely rare to find them in practice. In real life, in practical situations, we are actually dealing with random signals. This is because any given signal in real life is inevitably corrupted by the presence of noise. So as you can see, for example, in this particular GIF, this signal is a random signal. We cannot essentially describe the values of this particular signal corresponding to a given instant of time using a mathematical function in a precise manner. There is some given uncertainty or randomness that is inherent in this given signal. So we can state without doubt that all real life signals are random in nature. As a result of which, the techniques that we have developed until now to deal with the mathematical functions corresponding to the deterministic signals cannot be used in this realm of randomness at all. So how do we deal with these real-life random signals at all? Herein comes in the concept of statistical signal processing. So let us discuss first of all as to what is signal processing. Signal processing is generally concerned with the extraction of information from the input signal. Informally, signal processing is an intentional operation that is performed on a signal generated by a process. The input signal so as to produce a new signal, which is the output signal. And statistical signal processing is essentially the signal processing of random signals, the real life signals. And as the name suggests, this processing of random signals is accomplished using statistical tools and techniques. So for example, as you can see in this particular figure, we have electroencephalogram signals. So an electroencephalogram signal, which is essentially a brain signal, is a random signal. So any particular EEG waveform, or rather any particular EEG signal, can take any waveform from a multitude of possible waveforms. Say for example, it can be this waveform or this or this or this or this, or any given waveform from a particular ensemble of waveforms. And as a result, in order to deal with, for example, these EEG signals, which are the random real life signals, or in general any given kind of random signals, we need some given kind of statistical tools and techniques which revolve around the fundamental concepts of probability and random variables. And when we essentially discuss and when we quantify the notions of probability and random variables, in order to deal with the signal processing of random signals, we define a concept of random or stochastic processes. However, before we begin to dive deep into probability and random variables, let us first discuss the two main approaches which are generally followed by people who are working on in the domain of statistical signal processing. The first approach is that of estimation. Estimation theory in statistical signal processing essentially revolves around the determination of the signal waveform or other aspects of the signal, such as the parameters of the given signal. Estimation theory essentially revolves around finding the optimal approach, that is the best approach for the extraction of the necessary information from any given signal of interest. This best or optimal approach is not necessarily the exact approach. For example, in the case of estimation theory, we would be concerned with designing filters in order to remove artifacts, which are essentially nothing but interference and noise from EEG signals. The second approach adopted by practitioners of statistical signal processing, and in fact this is another domain altogether in the broad domain of statistical signal processing, and that is detection theory. Detection theory is essentially concerned with the determination of the most consistent model among a set of candidate models for data generation and measurement pertaining to a given set of data. For example, we could be concerned with the detection of zeros and ones from a received binary signal from a digital communication system. In fact, this received binary signal from a digital communication system is inherently corrupted by noise. It is a real live signal. And therefore, again, both the detection as well as estimation revolve around optimal approaches. However, when it comes to estimation theory, people can easily define the error metric in numerous ways. And as a result, this optimal approach that we are talking about essentially has different definitions for different people altogether. So say, for example, we use different error metrics in estimation theory, such as the mean absolute error, the mean squared error, or the root mean squared error. And corresponding to all of those error metrics, we can generate different optimal estimates for the same given problem. However, as can be proved via the statistics involved in detection theory, which essentially generates nothing but decision rules in order to determine the most consistent model, the fundamental nature of the decision rule does not change when we change the optimization criterion. So essentially, in other words, what this means is that a single optimal detector would minimize all the rational error criteria. Therefore, all this leads us to conclude that detection is science, whereas estimation is nothing but an art. Now that we have talked about the basic approaches in statistical signal processing, let us come on to the definition of a random variable. A random variable, which is denoted by x, is essentially a mapping, a function which maps points from the sample space omega to points in the real space R. And now that we have defined a random variable, which would further help us in defining the concept of a random process, we would also be required to define certain probability measures associated with a random variable so that we can, to some given extent, quantify this randomness. The first probability measure which we define is the cumulative distribution function, or the CDF, which is denoted by fx of small x, and it is essentially the probability of this random variable x taking on a value less than or equal to small x, wherein x is an element of the real dimensional space, that is a real space. So this cumulative distribution function is essentially a continuous smooth function in the case of continuous variables generally. However, in the case of discrete random variables, it assumes the form of a staircase. In the case of discrete random variables, however, we can define simpler measures as compared to the CDF. So, because in the case of CDF, we would be required to quantify the probability of this random variable taking on all the values as in or equal to a particular value x in the real space. However, in the case of discrete random variables, what is essentially the case is that a given random variable can only take on a particular value from a given finite set of values, which have already been defined beforehand. Therefore, we define the probability mass function, or the PMF, in the case of discrete random variables such that Px of x denotes the PMF and it is equivalent to the probability of that random variable x taking on a value x in the real space such that this particular value x belongs to the finite set of possible values which this particular random variable x can essentially assume. Further, in the case of continuous random variables, we can again go on to define another probability measure, which is a probability density function, or PDF. And this definition essentially of the probability distribution function would only hold true when the CDF is smooth and it is completely differentiable. And as a result, fx of x can be defined as the derivative of the CDF with respect to x. This was all the case for a single random variable. However, when we deal with statistical signal processing in real life, we are most often concerned with jointly distributed random variables. Essentially, we consider multiple random variables, say for example n random variables which are defined over the same sample space omega, and therefore in that case we define a random vector of random variables, n random variables, which is denoted by bold x, which maps from the sample space omega to the n-dimensional real space. So previously, while we had the random variable which mapped from the sample space to the one-dimensional real space, now we have the random vector which maps from the sample space to the n-dimensional real space. And so analogous to the probability measures which we defined in the case of a single random variable, in the case of jointly distributed random variables, we define number one, the joint CDF, which is the probability of this random vector taking on a set of values that is less than or equal to a given vector of values in the n-dimensional real space. The joint PMF for jointly distributed discrete random variables is defined as the probability of this random vector x taking on a vector of values in the n-dimensional real space from a given set of vectors of values in the n-dimensional real space. That is only the possible set of vectors that this particular x can be. And then we define the joint probability density function as the nth order partial derivative of the CDF with respect to x1, x2, so on and so forth till xn. And another important concept which we often talk about in statistical signal processing is statistical independence of random variables. Essentially, for example, two random variables are considered to be statistically independent, and this in fact holds true for the case of n random variables as well, that their joint CDF must essentially be separable. That is, for example, if we analyze the case of only two random variables, then fxy of x comma y must be equal to fx of x times fy of y. That is the product of their individual CDFs. Expectation, correlation, and covariance. Consider a random vector which maps from the sample space omega to the n-dimensional real space, and an arbitrary function g which maps from the n-dimensional real space to the one-dimensional real space. The expectation value of this function g is then going to be given by e of g of x is equal to the integration of g times the probability density function over the n-dimensional real space. And this particular integration over the n-dimensional real space essentially defines or essentially denotes n consecutive integrations from minus infinity to plus infinity. And thus the expectation value of x would be given is essentially identical to the mean of x, which we define as the expectation values of the individual members of this particular random vector, the individual random variables. Then we also go on to define the correlation matrix R of x, which is Rx, which is given by the expectation value of x transpose. And in fact, another important result is that independence of random variables implies their uncorrelatedness, but the converse, the fact that uncorrelatedness implies independence, may not necessarily be true in general. Next, another important concept which is defined in a manner analogous to variance is the covariance matrix Cx, which is defined as the expectation value of x minus mu x times x minus mu x whole transpose. Now that we have all this brief background of probability, random variables, expectation, correlation, and covariance, we can define a random process. A random process is essentially, again, a mapping denoted by x of t comma xi, wherein t, which is the index variable, is an element of a set capital T, and xi is an element of the sample space omega. So all these points in the sample space, say xi1, xi2, so on and so forth till xi k, are going to be mapped on to these waveforms x1 of t, x2 of t, so on and so forth. So for example, till xk of t, wherein t is an element of capital T. Essentially, all of the processes in real life are random in nature. And a very good simple example of this would be, for example, the flipping of an unbiased coin. Because it can either be a head or a tail. That is, the outcome is completely random. Now that we have defined a lot of the foundational statistics, let us come on to one of the approaches and discuss that in brief as well. So let us discuss the case of parameter estimation and estimation theory. So given a set of n observations or random variables, we can easily represent them by using a random vector x, which maps points in the sample space omega to the n-dimensional real space Rn. Now, corresponding to this random vector x, we have an observed data vector small x, which is again an n-dimensional vector, and this small x, which essentially corresponds to the observed values of these random variables in this random vector. And this observed data vector x can therefore be thought of as a realization of this random vector x. Now, this random vector x is characterized by joint probability density function, which depends upon, say, a parameter vector theta, which we refer to as the estimate. And therefore, the joint PDF is fx of x parameterized by theta. And the aim over here is to find the estimator, theta cap of x. So we know that it is a function of the random variable x, such that when theta cap operates on x, because it is essentially a function, it should, for x taking on these observed values small x, generate the estimates of the parameter vector as this theta, which is the actual estimate. Now, the properties of a good estimator, theta cap of x, are number one, unbiasedness. That is, the expectation value of the estimator should be equal to the actual estimate. However, we note that unbiasedness is not a criterion which guarantees the fact that the estimation error, that is the difference between the estimator and the actual estimate, is when it operates on this random vector, is the minimum. In fact, we can even have cases wherein biased estimators can have lower values of estimation error as compared to these unbiased estimators. Next, we come on to the case of consistency, in which case we note that the mean squared estimation error, the limit of that mean squared estimation error, the asymptotic limit, that is, when the number of the observations tends to infinity, this mean squared estimation error must essentially tend to zero. And efficiency, that the mean squared estimation error must be equal to m, wherein m is the Kramer-Rao bound. We note that it is the greatest or the largest possible value of the lowest bound of the mean squared error. And therefore, in this particular case, we note that if any given estimator is efficient as defined in this particular sense, then there is by no means existent another estimator which can produce a lower value of the mean squared estimation error as compared to the value of the mean squared estimation error generated by this particular estimator, which satisfies this particular condition. Now, some of the common parameter estimation techniques would include the maximum a posteriori method, the maximum likelihood method. There are also Bayesian methods which exist in the least squares method. Say, for example, we can consider just the maximum likelihood estimation case for discussion. And this revolves around the maximization of the likelihood of the, that is essentially nothing, the likelihood is nothing but the joint PDF fx of x parameterized by theta, and this essentially generates an estimator theta cap MLE such that this joint PDF is greater than or equal to the joint PDF when we use any other estimator apart from this estimator generated by the MLE. This is generally used when the a priori density of a parameter is unknown. It is this maximum likelihood estimation essentially generates a good estimator and is generally a preferred parameter estimation technique as well in this case, when because of the following reasons. Number one, that it is at least asymptotically unbiased, it is consistent, and we also note that it is asymptotically efficient. The maximum likelihood estimation technique is used, for example, to isolate the main signal from that particular same signal which has been corrupted by Gaussian noise. So say, for example, you have a discrete time random process which models the signal. So this discrete time random process is denoted by x of n and it is corrupted by Gaussian noise, say g of n, and this gives rise to the real signal which we actually observe, and that is again another discrete time random process, say y of n, and the goal over here is to isolate x of n from y of n, and maximum likelihood estimation would essentially ensure that when theta cap operates on y of n, it essentially generates x of n. However, all of these conventional SSP techniques fail in this present era of big data, right? In this present era of big data, these conventional SSP techniques are not that frequently used because they suffer from three major disadvantages. Number one, that obviously, in order to characterize all the real life complicated processes, it is inevitable that it is essentially impossible for us to have all data which can generate a particular functional mapping or which can generate an accurate estimate of any given parameter pertaining to that particular signal, or help us even in isolating that particular signal. This implies underdeterminacy of a given system of equations that that particular statistical signal processing technique may may essentially be solving, and as a result, this essentially cannot completely characterize any particular real-life complicated process to a very great accuracy. It's generalization accuracy, that is when we use, for example, that same statistical signal processing technique to another set of similar data in the same domain as that of the previous data is extremely less when we deal with large volumes of data that we have nowadays. Next, as we have already noted previously, these statistical learning algorithms, which have been traditionally used over this over the period of years until now, um, until the data set size reaches up to a particular value, which is essentially moderately small, these statistical learning techniques essentially build a model which continues to increase in efficiency and performance. However, as this data size increases, the efficiency finally saturates, right? They simply fail to scale with a sufficiently high value of efficiency. And finally, their non-reusability is again a very big problem, right? When you deal with any given set of data, for example, and say, for example, you've generated an estimate of the parameters pertaining to that particular signal, which is essentially going to correspond to that particular data. Now, say, for example, a month down the line, you are again working on that same particular process which generated that original signal, and then you generate a new set of data. Then in that particular case, when you need to add that particular set of data to the original set of data, the estimate of the parameter vector, which had initially been derived using these SSP techniques, can now not be used for the same case. And in fact, we cannot just simply build up from some particular high level of that particular SSP technique. We need to start from scratch. Because of all of these drawbacks, these SSP techniques are not used. And what is the solution? The solution is to turn to artificial intelligence techniques. Essentially, artificial intelligence is a term which has been coined by John McCarthy in 1956, and it deals with the simulation of intelligent behavior by computing machines. As propounded by Deptt and others in 1998, an intelligent agent does what is appropriate for its circumstances and goals. It is flexible to changing environments and changing goals. It learns from experience and it makes appropriate choices given perceptual limitations and finite computation. So AI resolves all of these problems which were essentially there in the case of conventional SSP techniques to a great extent. So say, for example, when we deal with sparsity, with the help of training, validation, and testing in an iterative fashion again and again, it's the generalization ability of these AI models, ML models, and in particular, we talk about the case of deep learning models, which are the most powerful models, the neural network models. Their generalization capability is very, very high when they are fed with large amounts of data. And so this remarkable fact about these deep learning neural network models is that they simply scale to very, very high values of efficiency when the size of the data set increases. And so they simply perform better when the data set size increases, in contrast to these traditional statistical learning algorithms. And the fact is that we can also implement transfer learning and even online learning, wherein we can already again add new examples which we found out pertaining to a particular process, and therefore there is no need to begin from scratch and repeat that analysis again and again. Let us demonstrate the usage of this of an artificial intelligence technique, wherein we are going to use an artificial intelligence model, in particular a deep learning model, a neural network, for some particular parameter estimation for a discrete time dynamic system. So consider a discrete time dynamic system. So you have a discrete time dynamic system wherein the output of the system y of k plus 1 depends upon a previous value of the input, that is u of k. Now it is known a priori that there is a delay in the system, and thus y of k plus 1 depends not only upon u of k but also on the previously generated outputs by the system, that's at the previous instance of time, that is y of k and y of k minus 1. The problem at hand is that we need to estimate the magnitude of the weights of these delayed outputs which are used as inputs by the system, so that we can essentially get an idea as to how much, as to by what amount does this output at any given instant of time t plus 1 depends upon the outputs generated by the system at previous instance of time t and t minus 1. So y of k plus 1 essentially can be given by w1, which is weight 1 times y of k plus w2 times y of k minus 1 plus w3 times u of k. And the solution to this particular system which we use would be, in this particular case, I would be considering a recurrent neural network, because essentially this particular dynamic system can easily be very well modeled in a recursive fashion, wherein we use the outputs generated by a system in previous instance of time in order to generate a new output, and therefore recurrence relations or recurrent neural networks which possess rich temporal characteristics are the most suitable models to be used in this regard. We use the following recurrent neural network, which has a single neuron, and therefore in this particular case we wish to determine these weights w1 and w2 in order to update the weights of this particular recurrent neural network, because the goal of this particular problem is to minimize the mean squared error, that is e of t plus 1, which is equal to half times y actual of t plus 1 minus the y of t plus 1. This y actual is the actual output of the given model, and this y of t plus 1 is the predicted output, and we are required to minimize the difference between the two such that finally this predicted output is equal to the actual output, and in doing so we would be able to find out the best possible or the most accurate values of w1 and w2 over here. In order to do so, we'd be using real-time recurrent learning, which is an online learning approach, in which case the gradient information is propagated forward at any given instant of time t, and this is much more efficient as compared to the conventional backpropagation approach, which is used in, say for example, simple fully connected neural nets. Weights are updated in this real-time recurrent learning algorithm or RCRL algorithm using the gradient descent algorithmic approach. So essentially wi of t plus 1 is equal to wi of t minus eta times the partial derivative of e of t plus 1 with respect to w sub I. So eta over here is the learning rate, and we are essentially going to update these weights in the direction of the steepest descent in order to minimize the MSE. Now this partial derivative of e of t plus 1 with respect to w sub I is equal to, using the chain rules in which we already know from calculus, the negative of y actual of t plus 1 minus y of t plus 1 times the partial derivative of y of t plus 1 with respect to w sub I. We define p sub w sub I at t plus 1 as being equivalent to the partial derivative of y of t plus 1 with respect to wi, and this yields the following weight, the following update laws for these PWIs of t at instance of time t plus 1. Now, I had essentially coded all of this in MATLAB, and these were the results that I had finally obtained. So the training set error is as low as of the order of approximately 10 raised to the power minus 29. This is indeed quite a low error, and thus, as can also be clearly seen from this learning curve as well, this MSE has the mean square error has decreased to a great extent over these 5,000 epochs, which is the maximum number of epochs for which I trained this recurrent neural net, and as a result of which this is going to be yielding a very good estimate of the actual system at hand. Therefore, the values of W1, W2, and W3, and in particular we were only interested in W1 and W2, minus 0.5 and minus 1, give us a very, very accurate estimate of the values of the weights corresponding to the delayed outputs, which were y of k and y of k minus 1, in determining the output y of k plus 1. And so, as we can also see from this particular plot as well, the predicted outputs, which are red outputs, are almost overlapping with the target outputs. We can actually not even uh, discern the predicted outputs from the target outputs over here, because the overlap between these blue and red circles is almost perfect in almost all of these cases, right? The MSE was of the order of 10 raised to the power minus 29. And so RNNs are essentially powerful in the sense that they have a very, very high accuracy and they converge very fast as well. And in particular, this analysis was only conducted for a set of 10 observations, which is quite small. However, in real life, when this is dealt with in terms of large volumes of data, RNNs perform much, much better, and in fact, very efficiently as compared to the conventional SSP techniques as well. So, I would just like to say that the future of statistical signal processing techniques is essentially going to be the artificial intelligent techniques. So this was all from my side for today, and these were the references that I'd followed for learning about statistical signal processing, and thank you.